A 2 cubic meter ideal gas has a temperature of 20 degrees Celsius at 1 atmospheric pressure, or 1 atm. The gas is then compressed to one half of its volume, and its pressure becomes 2.5 atm. What is the new temperature of the gas? So, we know that there is this equation where the pressure times the volume is equal to the number of moles in the gas times R, a gas constant, times the temperature of the gas. And this is the ideal gas law. And we can use this to solve our problem. So, we know that the initial pressure times the final pressure is equal to the number of moles in the gas times the gas constant times the initial temperature. The same thing can be said for the gas after it is compressed. So the final pressure is different, the final volume is different. But the amount of gas and the gas constant, these are the same, both before and after, since no gas is added or removed, and the gas constant always stays the same. And of course, the temperature is different too, as we're trying to calculate that. So we can both rewrite this equation. We can rewrite these two equations, saying that the initial pressure times the initial volume over the number of moles times the gas constant times the initial temperature is equal to 1. And the same thing can be said for the second equation, that it also equals 1. And since both of these equations equal 1, we can substitute this in for 1. And you could do this either way. So these two equations are going to be equivalent. Sure. The final pressure times the final volume divided by the number of moles times the gas constant times the final temperature. Now if you notice, these two are the same in both, so we can cancel these out. So you get that the initial pressure times the initial volume over the initial temperature is equal to the final pressure times the final volume over the final temperature. And this is true for all ideal gases. So I'm going to erase this to make more room. So I'm going to quickly list some of our variables here. The initial pressure is 1 atm, or the pressure of 1 atmosphere, our atmosphere. The initial volume is 2 cubic meters, and the initial temperature is 20 degrees Celsius, which we actually need to convert to Kelvin, which is 293 degrees Kelvin. Remember, Celsius is equal to Kelvin minus 273, or Kelvin is equal to the degrees Celsius plus 273. And that's how we can convert the units. And then the final pressure is given to us as 2.5 atm. The final volume is given to us as 1/2 of the initial volume, which is simply 1/2 of 2 cubic meters, which is 1 cubic meter. And the new temperature is what we're trying to solve for. So we can rewrite this equation and solve it for temperature. So you get that the final temperature is equal to the final pressure times the final volume divided by the initial pressure times the initial volume divided by the initial temperature. And so we can move this initial temperature up here to get our final equation. Now we just need to plug everything in. The final pressure is 2.5 atm. the final volume is 1 cubic meter. The final and the initial temperature is 293 degrees Kelvin. And we're going to divide that by the initial pressure of 1 atm times the initial volume. The initial volume is 2 cubic meters. And now all we need to do is just evaluate that equation there. So I'm going to erase this. So if you solve this, you should get that the final temperature is equal to 366.25 Kelvin. So 366.25 degrees Kelvin. And this is this is actually equal to 93.25 degrees Celsius. And that is how you would solve this problem here.